I'm going to work through how you'll do web assign 5 question 4, which is very similar to question 5 on the web assign. This problem is a little bit trickier than the ones from the lecture notes because in this problem you're trying to solve for TF. That will require a little more algebra, but overall the concept is exactly the same. To start with, I'm going to highlight in the problem as I go the two different substances. So I have 151 grams of water at 74.5 degrees Celsius. So those two numbers go together. And they're mixed with 76 grams of water at 21.5 degrees Celsius. So that's our other substance in this problem. It's also water, but it's at a different mass and different initial temperature, so it's like our second substance. If no heat is lost to the surroundings, what is the final temperature of the water? So I want TF. The specific heat of water is 4.184 joules per gram degree Celsius. The specific heat of any substance is the same as long as you're in the same state of matter. So liquid water will always be 4.184 joules per gram degree C. For this problem, I have information for water at one temperature and water at another temperature, and then I'm mixing them together. So the heat is going to flow from the water that's starting out at a higher temperature to the water that's starting out at a lower temperature until they come to thermal equilibrium or until they reach the same final temperature. So in this problem, the TF is the same for both waters. To start with, I'm going to identify my variables. So I'm going to do water 1 and water 2. And so water 2 is the pink stuff, and water 1 will be my green, just to keep track of them. All right, so for water 1, my mass was 151 grams. My C is 4.184 joules per gram degree C. My TI, that's the initial temperature, was 74.5 degrees C. And my TF is the unknown. So that's what I'm solving for. I will do the exact same thing for my other water. For the other water, my mass is 76.0 grams. My C is the same because it's still liquid water, so that is 4.184. My initial temperature is 21.5 degrees Celsius, and my final temperature is what I'm solving for. And remember, in this problem, because the heat is going to flow from the hotter to the cooler substance, and the heat will continue and flow until thermal equilibrium is reached. These two TFs are the exact same value. So we're going to solve for a single final temperature in the end of the problem. All right, now if I was to plug these all into my Q equation, I will have Q equals 151 grams times 4.184 joules per gram degree C. All of that times delta T. I like to leave delta T in the equation to kind of work on it, just because I think it's easier than having all the subtraction signs right from the beginning. For the other side, Q will equal 76.0 grams times my 4.184 joules per gram degree C, and then times, again, delta T. I'm just going to leave as delta T for now. In this problem, all right, so I have all of my numbers plugged in. The heat that is lost by one of the waters will be gained by the other. So to set that up, I will say that the Q of water 1 is equal to the negative Q of water 2. The amount of water stays the same. The sign just, or the heat value stays the same. The sign just changes. All right. So since those two are equal to each other, I'm going to set the two expressions equal to each other just by changing the sign. So I will have 151 grams times my 4.184 gram degrees C times my delta T for the first water, and that is equal to negative 76.0 grams, also multiplied by the same specific heat because it's still liquid water, and then this is times delta T2. All right. I'm going to do some math to make my solutions a little bit easier. So I'm going to multiply 151 times 4.184. That will give me 631.784 times delta T1. And that will equal, I'll multiply 76.0 times 4.184. So that on this side will give me negative 317.984, which gets multiplied by delta T2. All right, so now that I've gotten that, I'm going to isolate one of the t's. It does not matter which one I do. I just think that this will make my math easier in the long run. So I'm going to divide both sides by negative 317.984. All right, so now my expression is negative 1.9868 delta T1 equals delta T2. All right. The change in temperature of water 1 does not equal the change in temperature of water 2. The final temperature is the part that's the same. So now I'll plug back into, for each delta T, the TF minus TI. On the left, I have negative 1.9868 times TF minus 74.5 degrees C. And then on the right side, I will have TF minus 21.5 degrees C. So I have TF on two separate sides of the equation. I have TF here, TF here. So this will require me to do some algebra and then combine like terms. So I'm going to distribute the negative 1.9868 to the other pieces within the parentheses. So I have negative 1.9868 TF plus, because a negative and you have subtraction, so in the end it's plus 148.0197 equals, and then on the other side I still have TF minus 21.5 degrees C. All right. I'm going to start by adding 21.5 to both sides. All right, so when I do that, I will now on the left have negative 1.9868 times TF plus 169.5 equals TF on that side. And now this is really like 1 TF, remember? So it's like there's a 1 in front of it. So now I need to add 1.98, oh, that's messy, add 1.9868 TF to both sides. All right, so I will get that 169.5 equals 2.9868 TF, and then divide both sides. by my 2.9868 to isolate TF. And really, I carried a lot of extra sig figs along the way just so I wouldn't make an error in rounding. In the end, I am not going to be very stringent on your sig figs in this type of math. There's too many steps all along the way. I tend to just match however many digits the initial temperature was given, assuming you're using the same device to measure the temperature at the initial point and the final point. So if you're using the same instrument, you would go to the same number of decimal places because that's where the accuracy of that will be. So in the end, my get on my example, 56.7 degrees C is my TF. All right, so this will be the exact same process you would use if you had two different metals. You would just have two different C values along the way. The only reason I have the exact same C value for both my substances was because they were both liquid water. So they have the same specific heat that we're dealing with. But in any other problem, you'll just set up your two separate ones, and then you'll have to distribute, combine like terms, and do all your math. So again, the setup really isn't that much different than if you were solving for one of the missing masses or one of the missing specific heats. The only difference is the algebra is a lot harder when you're missing the final temperature.